Right now, as you read this, the Milky Way contains somewhere between 200 billion and 400 billion stars. That number is difficult to hold in your mind, so consider it this way. If you tried to count every star in our galaxy, one per second, without sleeping, without stopping, without pausing for a single breath, you would need approximately 6,000 to 12,000 years to finish. You would have started before the first Egyptian dynasty built its first monument. You would still be counting now, and when you finally reached the last star, you would have counted only the stars of one galaxy in a universe that contains somewhere between 100 billion and 2 trillion galaxies. The universe is not large. The word large does not contain enough space to describe what the universe is. It is a structure so incomprehensibly vast that every attempt to visualize it collapses into abstraction before it can take shape in a human mind. And yet, within that structure, across those hundreds of billions of galaxies, each containing hundreds of billions of stars, many of them circled by planets, many of those planets sitting in the narrow temperature bands where liquid water can exist, where chemistry can organize itself into complexity, where complexity can organize itself into life. Across all of that, we have found exactly one place where something looks back at the stars and wonders about them. 1. Us. This should not be the answer. Every calculation, every estimate, every reasonable application of the probabilities we understand points toward a universe that should be teeming with voices, with signals, with the unmistakable signatures of minds that have been building, transmitting, and expanding for millions or billions of years longer than we have. The math does not predict a silent universe. The math predicts a universe so full of life that the silence should be impossible, and yet the silence is all we have ever found. For more than 60 years we have been listening. We have pointed radio telescopes at thousands of stars. We have scanned billions of frequencies. We have sent our own signals outward and waited for a reply. We have found planets by the thousands, some of them rocky, some of them at the right distance from their stars, some of them bearing the faint spectral signatures of water and atmosphere. We have learned that the building blocks of life, amino acids, organic molecules, the chemical precursors to biology, exist not just on Earth, but in interstellar clouds, in meteorites, on the surfaces of comets. The universe appears to want to make the ingredients, it appears to provide the conditions, and then, somehow, it falls silent. This is the Fermi paradox, not a paradox in the technical logical sense, but a paradox in the deeper sense, a collision between what we expect and what we observe, a gap so wide and so strange that it has consumed the professional lives of physicists, astronomers, biologists, philosophers, and every variety of scientist who has ever looked up at a dark sky and asked the question that feels increasingly urgent the longer it goes unanswered: where is everybody? If you have ever stood outside on a clear night and felt the particular weight of that darkness pressing back against you, you already understand something of what this question contains. It is not simply a scientific puzzle. It is a question about the nature of existence itself, about whether the universe that produced us considers us remarkable or routine, about what it means that we are here, aware, wondering, reaching outward with instruments and mathematics and radio waves, and finding nothing that reaches back. If you enjoy journeys that take you to the edge of what science knows and then one step further into what it cannot yet answer, do me a small favor and hit that like button and subscribe. It genuinely helps this channel reach more people who want to think about these things seriously. Now, find somewhere comfortable. Let the room go quiet around you. What we are about to explore will not give you easy answers. It will give you something more valuable than that. It will give you the full weight of the question. Let's begin. The story has a specific starting point, not in an observatory, not in a classified government facility, not in the pages of a scientific journal. It begins at a lunch table, Los Alamos, New Mexico, the summer of 1950. The men sitting around that table were not ordinary men by any reasonable measure. They were physicists who had spent the previous decade building the most destructive weapon in human history. They had seen the Trinity test in the desert. They had watched a fireball rise over the Jornada del Muerto. and understood, in a way that very few human beings ever would, exactly what the energy of a nuclear reaction looked like when released all at once into the open air. They were, by temperament and training, people who thought carefully about large questions and uncomfortable answers. That summer, there had been a wave of newspaper stories about flying saucers, unidentified objects in the sky, public excitement, and official skepticism in roughly equal measure. The physicists at lunch had been joking about it, trading comments with the kind of dry wit that people who spend their lives around numbers tend to develop when faced with popular enthusiasm for things that numbers cannot easily support. Enrico Fermi, by this point, was among the most celebrated physicists alive. He had built the first nuclear reactor beneath the bleachers of a Chicago football stadium in 1942. He had won the Nobel Prize in Physics in 1938. He had a reputation among colleagues for what they called Fermi estimation, the ability to produce surprisingly accurate answers to seemingly unanswerable questions through careful reasoning from first principles. How many piano tuners are there in Chicago? How many atoms are in a grain of sand? What is the yield of this explosion? Fermi would work through the problems systematically, estimating each component, multiplying the estimates together, and arriving at a number that was usually close enough to the truth to be useful. And then, in the middle of the lunch conversation, Fermi went quiet for a moment. He had been thinking, and the thought had taken him somewhere that the conversation had not expected to go. He looked up and asked, with the casual certainty of a man who had just worked through a calculation in his head, a question that has echoed through the scientific community ever since. "But where is everybody?" The table understood immediately what he meant. Not the flying saucers, not the newspaper stories, the real question behind all of it. If the galaxy is as old as it is, if it contains as many stars as it does, if even a small fraction of those stars have planets, and even a small fraction of those planets have life, and even a small fraction of that life becomes intelligent, and even a small fraction of that intelligence develops technology, then the numbers suggest that spacefaring civilizations should have been out there for an enormous amount of time before us, long enough to have spread across the galaxy many times over, long enough to have left unmistakable evidence of their existence, long enough that their absence from our sky, from our radio receivers, from our instruments, from every measurement we have ever made of the universe around us is not a neutral observation. It is a data point, and it is a deeply strange one. The Milky Way is approximately 100,000 light-years across. Our galaxy formed roughly 13.5 billion years ago, nearly as old as the universe itself. The universe is 13.8 billion years old. For the vast majority of galactic history, the conditions necessary for complex chemistry, stable planetary systems, and long-term biological evolution have existed. Stars with the right elemental composition, planetary systems with rocky inner worlds, enough time for evolution to work. If a civilization had arisen somewhere in this galaxy just 1 million years before us, which on cosmic timescales is a rounding error, a civilization indistinguishable in age from our own in any photograph of the universe, and if that civilization had developed the capacity for interstellar travel at even 1% of the speed of light, it could have crossed the entire diameter of the Milky Way in 10 million years. Not in a straight line necessarily, not in a single mission, but through the slow, systematic expansion of a space-capable species hopping from star to star, establishing outposts, sending out probes, filling the available volume of the galaxy the way a gas fills an empty container. 10 million years sounds like a long time. It is nothing. The dinosaurs ruled this planet for 165 million years. 10 million years is a fraction of that. It is a moment in geological time. It is barely a heartbeat in cosmic time. A civilization 1 million years older than us, expanding at 1% of light speed, would have had ample time to visit every star system in the galaxy, multiple times. It would have had ample time to build structures visible from other star systems, to alter the electromagnetic output of stars, to seed life on promising worlds, to leave artifacts on every rocky planet it encountered, to fill the galaxy with signals so dense and so varied that a species with a simple radio telescope could not possibly miss them. And we have missed nothing because there is nothing to miss. This is the central strangeness of the Fermi paradox. It is not simply the absence of confirmed alien contact. Contact requires proximity and a kind of cosmic coincidence that may not be expected. What is strange, what is genuinely difficult to explain, is the absence of any detectable signature of any technological civilization anywhere in our observable universe across 13.8 billion years of cosmic history, despite the fact that the conditions for life appear to be widespread, and the timescales involved more than sufficient for any sufficiently motivated civilization to have become impossible to overlook. The silence is not empty. It is full of implication, and the implications are not comfortable. There is a version of this question that sounds reassuring when you first encounter it. Maybe, the argument goes, we simply have not been looking long enough, or carefully enough, or at the right frequencies, or with the right instruments. Maybe the universe is full of voices, and we are just beginning to learn how to listen. This version is appealing because it preserves the hope that the silence is temporary. That next year, or next decade, or next century, we will finally tune to the right channel and hear something that changes everything. But here is what that version consistently underestimates. The search for signs of technological civilization in the universe is not restricted to active listening for radio signals. It encompasses every measurement we have ever made of the universe around us: optical surveys, infrared observations, X-ray and gamma-ray astronomy, studies of stellar spectra, analysis of gravitational waves. The entirety of modern observational astronomy is, in a broad sense, a survey of whether anything in the universe shows signatures inconsistent with purely natural processes. And nothing does. Not one star whose output suggests artificial modification. Not one galaxy whose infrared excess implies a civilization harvesting its star's total energy output. Not one region of space where the chemical composition of gas clouds reflects industrial contamination on a civilizational scale. Not one repeating signal from any direction at any frequency bearing the hallmarks of intentional transmission. The universe has been observed across the entire electromagnetic spectrum, across billions of light years, with instruments of extraordinary sensitivity, and it looks exactly as it would look if biology had arisen exactly once, here on this small, rocky planet, orbiting an unremarkable star on the inner edge of the Orion arm of the Milky Way. That is the question Fermi asked at a lunch table 75 years ago, and it remains, as of this moment, unanswered. But the people who have spent their careers trying to answer it have not been idle. They have built frameworks. They have mapped the space of possible explanations. They have identified, with increasing precision, exactly where the uncertainty lives and exactly how much of it remains. And in doing so, they have transformed a casual lunch table observation into one of the most consequential unsolved problems in all of science. Because the answer, whatever it turns out to be, will tell us something about ourselves that nothing else can. It will tell us whether we are typical or exceptional, whether the path from chemistry to consciousness is easy or nearly impossible, whether the universe is a place that makes minds routinely, the way it makes stars and planets, or whether it has done so only once, producing a single candle burning in an otherwise lightless dark. To understand why this matters, and to understand why each proposed answer is more unsettling than the last, we need to begin where the scientific investigation of this question began, with a room full of astronomers, a blackboard covered in variables, and a man named Frank Drake who decided, in the autumn of 1961, that it was time to try to put a number on the question that everyone was thinking about, but no one had dared to formalize. Green Bank, West Virginia, November 1961. The town sits in a valley carved out of the Allegheny Mountains, surrounded by ridges that block radio signals from the outside world. This is not an accident. The National Radio Astronomy Observatory chose this location precisely because the mountains create a natural electromagnetic shield, a bowl of quiet in a country that was, even then, filling its airwaves with television broadcasts, radar pulses, and the growing electromagnetic noise of an industrializing civilization. In Green Bank, the silence is protected by geography and by federal law. The surrounding counties form the National Radio Quiet Zone, one of the few places in the United States where you cannot legally operate a microwave oven without a permit because the interference might contaminate the data collected by the telescopes on the valley floor. It is an appropriate place to listen for the universe. Frank Drake was 31 years old that November. He had spent the previous year conducting the first modern scientific search for extraterrestrial radio signals, a project he called Ozma, named after the princess of the fictional land of Oz, a place very far away and very difficult to reach. For approximately 200 hours between April and July of 1960, Drake had pointed the 85-foot radio telescope at Green Bank toward two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened at a frequency of 1,420 megahertz, the emission frequency of neutral hydrogen, the most abundant element in the universe. His reasoning was that any technologically sophisticated civilization attempting to communicate across interstellar distances might choose this frequency precisely because it was universal, a number written into the physics of the cosmos itself, a beacon that any species with a radio telescope would recognize as significant. He heard nothing from the stars. He did detect one strong, structured signal that briefly electrified the team before being identified as a classified military aircraft flying through the telescope's field of view. The excitement lasted approximately 10 minutes. Then it was gone, and the silence resumed. Drake was not discouraged, he was systematic. And in November of 1961, he organized a small conference at Green Bank, bringing together a handful of scientists to think seriously about the question of extraterrestrial intelligence. The attendees included Carl Sagan, then a young astronomer at the beginning of what would become one of the most influential careers in the history of science communication, John Lilly, the neuroscientist who had been studying dolphin communication and whose work suggested that intelligence on Earth was not as unique as commonly assumed, Melvin Calvin, a biochemist who would learn, partway through the conference, that he had just been awarded the Nobel Prize in Chemistry, and several others, each bringing a different discipline to a question that no single discipline could answer alone. To focus the discussion, Drake wrote something on the blackboard before the conference began. It was not a conclusion, it was not even a hypothesis in the conventional sense. It was a framework, a way of organizing ignorance into a form that could be examined, debated, and eventually filled in with data as science advanced. He wrote it as an equation because equations impose discipline on thinking. They force you to identify every component of a problem and assign it a value, even if that value is a range, even if that range spans orders of magnitude. The equation asked a single question: how many technologically advanced civilizations capable of interstellar communication exist in the Milky Way right now? And it proposed that this number could be estimated by multiplying together a series of factors, each representing one step in the long chain of events that must occur to produce a civilization capable of making itself known across the stars. The first factor was the rate at which new stars form in the Milky Way. This is the most constrained of all the variables. Astronomers have measured it with reasonable confidence. The galaxy produces somewhere between 1 and 3 new stars per year on average, though the rate has varied over cosmic history and was higher in the galaxy's youth. Call it approximately 1 to 3 new stellar nurseries per year, each one a potential anchor for a planetary system. The second factor was the fraction of those stars that have planets. When Drake wrote his equation, this number was almost entirely unknown. No exoplanet had been confirmed. The technology to detect planets around other stars did not yet exist in a practical form. Drake estimated, with appropriate uncertainty, that perhaps 1 in 5 stars might have planets. He was being cautious. In 2009, NASA launched the Kepler Space Telescope into an Earth-trailing orbit around the Sun. Over the following 9 years, Kepler monitored approximately 150,000 stars simultaneously, watching for the tiny, regular dimming that occurs when a planet passes between its star and the telescope. The results? published across hundreds of papers over more than a decade, revised Drake's estimate dramatically upward. We now know that planets are not rare companions to stars. They are the default. Nearly every star in the Milky Way has at least one planet. Many have multiple. The galaxy contains more planets than stars. This is one of the most significant empirical discoveries of the last quarter century, and it is entirely on the optimistic side of the ledger. The third factor was the fraction of those planets that could actually support life. Not just any planets, but planets with the right conditions, rocky surfaces, or at least a stable chemical environment. Temperatures that allow liquid water over long periods. Stable orbits that do not swing the planet from frozen wastes to baking deserts on a timescale that biology cannot accommodate. Atmospheric chemistry that provides the raw materials for organic reactions. Here, the uncertainty expands. We have detected planets in what astronomers call the habitable zone, the range of distances from a star where liquid water could theoretically exist on a planetary surface. The Kepler mission alone identified thousands of candidate habitable zone planets. But habitable zone membership is a necessary condition for life, as we understand it, not a sufficient one. Mars sits at the inner edge of our own sun's habitable zone and has been a frozen desert for 3.5 billion years. Venus sits closer to the sun but remains perpetually at temperatures hot enough to melt lead due to a runaway greenhouse effect that no organism we know of could survive. The fraction of habitable zone planets that are genuinely hospitable to life in a sustained way is deeply uncertain. Drake estimated somewhere between 1 in 10 and 1 in 2. Current thinking suggests something in a similar range, perhaps biased toward the lower end, as we learn more about how many ways a planet can be in the right place and still be the wrong kind of world. The fourth factor was the fraction of suitable planets on which life actually originates. This is where the uncertainty becomes genuinely vertiginous. We have exactly one data point: Earth. Life arose on this planet within, at most, a few 100 million years of the surface, cooling enough to allow liquid water. Given that life appeared so quickly once conditions permitted, some biologists argue that the origin of life is an almost inevitable chemical process, something that happens readily whenever the right ingredients and conditions are present, that it may occur on virtually every planet where it has a chance to take hold. Others argue precisely the opposite, that the origin of life required such an improbable sequence of chemical events, such a specific combination of molecules in such a precise physical context, that it may have happened only once in the observable universe, here, by a chance so remote that calculating its probability is essentially meaningless. Between these two positions lies almost everything science knows about abiogenesis, which is to say, not enough to confidently assign a number to this factor. Drake in 1961 assumed it might be close to 1, meaning life arises on almost every suitable planet. That assumption remains unverified. It remains one of the deepest open questions in all of biology. The fifth factor was the fraction of life-bearing planets that develop intelligent life. Again, one data point. Again, a question that cannot be answered by extrapolation from a single example. Evolution on Earth produced intelligence, but it did so through a process that appears to have taken approximately 4 billion years, and there is serious debate about whether intelligence was an inevitable outcome of that process, or a highly improbable one. The evolutionary path to human-level intelligence required an extraordinary sequence of contingencies. The emergence of eukaryotic cells, the transition from single-celled to multicellular organisms, the development of sexual reproduction, the Cambrian explosion of animal body plans, the rise of vertebrates, the extinction events that cleared ecological space for new forms, the particular lineage of primates, the particular branch of apes, the particular pressures that drove encephalization in one group of hominids over several million years. Alter any of those contingencies and intelligence as we know it may not arise. Stephen Jay Gould famously argued that if you rewound the tape of life and played it again from the beginning, the result would be profoundly different, and there is no guarantee that intelligence would emerge at all. Others argue that intelligence is such a powerful adaptation that convergent evolution makes it likely wherever complex life exists long enough. both arguments are plausible, neither is proven. The sixth factor was the fraction of intelligent species that develop technology capable of interstellar communication. This seems almost trivial if you have gotten this far in the chain. A species intelligent enough to develop civilization will presumably eventually develop radio technology, because radio is simply an application of electromagnetism, and electromagnetism is a fundamental feature of reality that any civilization advancing through physics will eventually encounter. But civilization is not guaranteed. A species can be intelligent without being technological. Dolphins appear to be highly intelligent. They have complex social structures, demonstrable problem-solving ability, and sophisticated communication. They have existed in roughly their current form for millions of years. They have not built radio telescopes. Intelligence and technology are not the same thing, and the transition between them required, on Earth, a very particular ecological context, an opposable thumb, a terrestrial environment where manipulating physical objects was advantageous, a social structure that accumulated and transmitted knowledge across generations, a climate that drove behavioral flexibility. How common that combination is across the universe is, once again, unknown. The seventh and final factor was the one that Drake himself considered the most uncertain and the most important. The average lifespan of a technological civilization. How long does a species capable of interstellar communication remain in that state? Not how long the species exists, but how long it maintains the technological and social capacity to make itself known across interstellar distances. This number is the one that determines everything. If a civilization typically survives for 10,000 years after developing radio technology, and if the Milky Way has been producing such civilizations for billions of years, then at any given moment there should be thousands of them broadcasting simultaneously, filling the radio spectrum with signals we should be able to detect. If a civilization typically survives for only a few centuries before destroying itself through war, ecological collapse, pandemic, or the particular fragility that appears to accompany the period when a species is powerful enough to destroy itself, but perhaps not yet wise enough to choose otherwise, then the number of active civilizations at any moment drops dramatically. Drake estimated this lifespan at 10,000 years. He arrived at that number partly from optimism and partly from the fact that if civilizations were short-lived, the search for them would be essentially hopeless. And Drake was not the kind of scientist inclined toward hopelessness. Multiply these factors together, and you get what is called N, the estimated number of detectable civilizations in the Milky Way right now. At the Green Bank Conference in 1961, working with Drake's estimates, the attendees arrived at numbers ranging from roughly 10 to 10,000 active civilizations in our galaxy at this moment. The variation reflects the range of reasonable assumptions, but the important point is that even the most conservative calculation using optimistic values for each factor tends to produce a number substantially greater than 1. The equation, taken at face value with reasonable assumptions, predicts a galaxy that is not empty. It predicts a galaxy populated with minds. And this is the moment where the equation stops being a source of comfort and starts being a source of dread. Because the Drake equation is not a prediction. It is a framework for organizing what we do not know. And what we do not know, it turns out, is almost everything. Every factor beyond the first two, the rate of star formation and the fraction of stars with planets, is either poorly constrained or essentially unknown. The equation allows you to produce any answer you want by choosing values within the range of scientific uncertainty. If you are an optimist, you choose the high end of every range and arrive at millions of civilizations. If you are a pessimist, you choose the low end and arrive at something close to 1. The equation does not resolve the uncertainty. It maps it. It shows you exactly where the ignorance lives, and it shows you, with uncomfortable clarity, that the ignorance is vast. What the equation does definitively is this. It demonstrates that the question of extraterrestrial intelligence is not a question of faith or speculation. It is a question of empirical values. Fill in the real numbers and you get the real answer. The problem is that we do not have the real numbers for most of the factors. And in the absence of those numbers, The equation cannot tell us whether the galaxy should be full or empty. It can only tell us that our assumptions about its fullness or emptiness have enormous consequences for how we interpret the silence. And there is something else the equation reveals, something that Drake himself recognized at Green Bank, and that has become more apparent with every passing decade of the search. The last factor, the lifespan of civilizations, dominates the calculation in a way the other factors do not. You can vary the biological and astronomical factors across their full range of uncertainty, and the total changes by perhaps a few orders of magnitude. But the lifespan factor can range from decades to billions of years, and that range alone determines whether we should expect zero detectable civilizations in the galaxy or millions. The fate of civilizations, the question of whether technological species tend to endure or tend to destroy themselves, carries more weight in the equation than all the astronomical and biological factors combined. Drake understood this when he assigned 10,000 years as his estimate. He was not making a scientific claim, he was making a moral argument. He was saying that civilizations can choose to survive, that the development of technology does not inevitably end in self-destruction, that intelligence, properly applied, is a path to longevity rather than extinction. It was an optimistic assumption dressed in the language of mathematics, and it remains, 60 years later, an assumption, not a measurement, not a confirmed value, an act of scientific hope. The conference ended with no consensus on the numbers, but with something more important. A shared understanding that the question was serious, that the search was legitimate, and that the silence, which had so far been absolute, was not evidence of absence, but evidence of ignorance. We simply did not know enough yet. The telescopes were too small, the searches too narrow, the time invested too short. The answer was out there, presumably, and with better instruments and more time, we would find it. That was 1961. We now have instruments of extraordinary sophistication that Drake could not have imagined. We have mapped the galaxy's star population with a precision that would have seemed miraculous to the scientists at Green Bank. We have confirmed the existence of more than 5,500 exoplanets and identified hundreds of them as potentially habitable. We have constructed the most sensitive radio receivers ever built and aimed them at thousands of candidate star systems across every frequency band that physics and Earth's atmosphere allow. We have sent our own messages outward, including the Arecibo message of 1974, a binary encoded transmission describing human biology and mathematics, and the location of our solar system, beamed toward the globular cluster Messier 13, approximately 25,000 light-years away. The silence has not broken, not once. Not a single confirmed signal, not a single repeating pattern, not a single structured transmission from any direction in the sky that has survived scientific scrutiny as something other than a natural phenomenon or a terrestrial artifact. The search has grown enormously in capability since Drake pointed an 85-foot dish at two nearby stars for 200 hours in 1960. And the silence has grown with it, more thoroughly documented with every passing year, more carefully characterized, more certain. Which brings us to the place that the Drake equation leads when you follow it all the way to its logical end. If the numbers should predict civilizations and the observations reveal none, then something in the chain is wrong. One of the factors, or several of them, must be dramatically lower than optimism suggests. The galaxy is not producing communicating civilizations at the rate the equation implies, at least not if communicating civilizations tend to persist. Something is suppressing the number. Something is filtering the chain between the formation of stars and the emergence of minds that reach across the cosmos. And finding that filter is the most consequential and most terrifying problem in science, because once you understand where it is, you understand something about where we stand in relation to it. Behind us, already in our past, a challenge we have apparently survived, or ahead of us, still waiting, a barrier that no civilization has yet found a way through. That question, and what it means for everything we think we know about our own future, is where we need to go next. There is a version of the Fermi paradox that resolves itself before it becomes a paradox at all. It is the version that most people reach first, instinctively, when they hear the question for the first time. The universe is enormous, this version says. The distances between stars are so vast that even if other civilizations exist, they simply cannot reach us, cannot signal us, cannot make themselves known across the immensity of space. The silence is not mysterious. It is a consequence of geometry, of physics, of the simple, brutal fact that the universe is too large and the speed of light too slow for anything to cross the gap between one civilization and another in any time frame that would allow contact. This version is comforting. It preserves both the existence of extraterrestrial life and the integrity of our solitude. We are not alone, it suggests. We are merely isolated, separated by distances so crushing that even the most advanced technology conceivable cannot bridge them within the span of a civilization's memory. It is a reasonable first response, and it is not wrong exactly. The distances are real. The constraint imposed by the speed of light is real, but it fails, on examination, to actually resolve the paradox, and understanding why it fails is essential to understanding why the Fermi paradox is as deep as it is. The nearest star to our Sun is Proxima Centauri, a small red dwarf approximately 4.2 light-years away. A light-year is the distance light travels in 1 year, moving at approximately 299,000 kilometers per second. At that speed, light crosses the distance between Earth and the Moon in about 1.3 seconds. It crosses the distance between Earth and the Sun in approximately 8 minutes, and it requires 4.2 years to travel from our Sun to its nearest neighbor. The Voyager 1 spacecraft, launched in 1977, and currently the most distant human-made object in existence, has been traveling for nearly 50 years at approximately 17 kilometers per second. At that speed, it would take approximately 73,000 years to reach Proxima Centauri if it were aimed in that direction, which it is not. These numbers make interstellar travel sound impossible. And for us, right now, with our current technology, it essentially is. But the Fermi paradox is not about us, right now. It is about any civilization, anywhere in the galaxy, at any point during the last several billion years. And the argument that distance makes contact impossible breaks down entirely when you apply it across cosmic timescales. Consider a civilization that develops interstellar travel capability, not at anything approaching the speed of light, but at 0.1% of the speed of light. That is approximately 300 kilometers per second, roughly 17 times faster than Voyager 1, and well within the realm of what physics permits using technology that is not wildly beyond our current understanding. Concepts like nuclear pulse propulsion, which was seriously studied under Project Orion in the 1950s and 1960s, could theoretically achieve velocities in this range. At 0.1% of light speed, a spacecraft would take approximately 42,000 years to reach Proxima Centauri. That is a long time by human standards. It is nothing by galactic standards. Now suppose this civilization does not travel itself, but sends self-replicating probes, small automated systems capable of traveling to a nearby star, using local resources to manufacture copies of themselves and dispatching those copies to the next set of nearby stars. This is not science fiction. It is a straightforward application of the same principles that govern biological reproduction and industrial manufacturing, applied to a context where the energy and raw materials are available in abundance at every stellar system. John von Neumann, the mathematician whose work underlies modern computing, described the theoretical basis for such machines in the 1940s. They bear his name, von Neumann probes. A network of von Neumann probes, expanding at 0.1% of the speed of light, reproducing at each star system they visit, would cover the entire diameter of the Milky Way in approximately 1 billion years. 1 billion years. The galaxy is 13.5 billion years old. If any civilization in the galaxy developed self-replicating probes at any point during the first 12.5 billion years of galactic history, those probes would have had time to visit every star system in the Milky Way, multiple times. The solar system has been here for 4.5 billion years. Any probe network launched more than 5.5 billion years ago would have reached us before Earth even formed. Any network launched since Earth formed would have had 4.5 billion years to arrive. We have found no probes. We have found no artifacts. We have found no structures, no signals, no modifications of our solar system that suggest a visit by anything other than the natural processes that physics and chemistry and geology produce on their own. The solar system looks exactly as it would look if it had never been visited. Distance, therefore, is not the answer. Distance buys time, but cosmic timescales render that time irrelevant. The galaxy is old enough and large enough that the absence of contact cannot be explained by the simple size of the space between stars. Something else must account for it. But before we reach the deeper explanations, there is one more piece of the physical picture that deserves careful attention, because while distance alone does not resolve the paradox, it does reveal something important about the nature of the challenge. And it introduces a concept that will thread through everything that follows. The speed of light is not merely a technical limitation, it is a fundamental feature of the structure of reality. Einstein's special relativity, confirmed by over a century of experimental tests to a precision that no other physical theory has matched, establishes that no information, no signal, no material object can travel faster than light through space. This is not a constraint that better engineering can overcome. It is not a barrier that a sufficiently advanced civilization could tunnel through with the right technology. It is a hard boundary written into the geometry of space-time itself. What this means for interstellar civilizations is that every one of them, regardless of how advanced, exists inside a bubble defined by its own light cone, a sphere of influence and communication whose radius expands at the speed of light and no faster. A civilization that has been transmitting for 1,000 years can be known, at most, to civilizations within 1,000 light-years of its position. Everything beyond that radius is causally disconnected from it, not just difficult to reach, genuinely unreachable in any time frame that allows a response within the civilization's lifetime. If you imagine the Milky Way as a disk, approximately 100,000 light-years across, and you place a civilization somewhere within it, the fraction of the galaxy that lies within 1,000 light-years of that civilization is approximately 1/10,000th of the total galactic volume. The vast majority of the galaxy is, for any given civilization transmitting for only 1,000 years, permanently beyond the horizon of possible contact. This does not make contact impossible over longer timeframes, but it means that the universe imposes a profound isolation on civilizations in their infancy. And if civilizations tend to be short-lived, that isolation may be permanent. There is something philosophically significant in this picture. Every civilization in the galaxy, if they exist, is having exactly the same experience we are having right now. They are sitting at the center of their own light cone, looking outward, finding silence, and wondering whether they are alone. The universe does not provide a view of its full contents to anyone. It provides a local horizon and nothing beyond it. We are all, if there is a we at all, islanders who cannot see past the curve of our own ocean. This brings us to a hypothesis that has quietly reshaped the scientific conversation around the Fermi paradox over the past 3 decades. It does not resolve the paradox by appeal to distance or communication delay. Instead, it cuts deeper. It asks whether the conditions that produced us are genuinely rare, not just uncommon, but vanishingly, almost impossibly rare on a cosmic scale. The rare Earth hypothesis was developed most fully by paleontologist Peter Ward and astronomer Joe Brownlee in a book published in the year 2000, though the underlying ideas had been circulating in scientific discussions for years before that. The core argument is this: the emergence of complex, multicellular, animal-grade life on Earth was not the product of conditions that are typical of habitable planets. It was the product of an extraordinary coincidence of factors, each individually uncommon, which in combination make Earth not a representative example of a life-bearing planet but an extreme outlier, a 1 in billions accident that only looks inevitable from the inside. Begin with location. The Milky Way is not uniformly hospitable to life. The galactic center, where stars are packed densely and supernova rates are high, is a region of intense radiation and gravitational chaos. A planet near the galactic center would be sterilized repeatedly by nearby stellar explosions, bombarded by X-rays and gamma rays from the supermassive black hole at the galaxy's core, and subjected to gravitational perturbations that would destabilize planetary orbits over time. The outer regions of the galaxy, conversely, are deficient in the heavy elements, carbon, oxygen, iron, silicon, that complex chemistry requires, because heavy elements are manufactured in stars and distributed through supernova explosions, a process that takes billions of years and has proceeded much further in the star-dense inner regions of the galaxy than in the sparse outer arms. Earth sits in what astronomers have called the galactic habitable zone, a ring-shaped region roughly 23,000 to 30,000 light-years from the galactic center, where heavy element abundance is sufficient for rocky planets and complex chemistry, and where the radiation and gravitational environment is calm enough to allow billion-year windows of stability. This zone is not tiny. It contains a substantial fraction of the galaxy's stars. But it is not the whole galaxy. Many stars lie outside it, in regions that are either too violent or too chemically impoverished to support the kind of planetary chemistry that produced life here. Now consider the Sun itself. It is a G-type main sequence star, what astronomers classify as a yellow dwarf. It is not particularly common. The most numerous stars in the galaxy are red dwarfs, M-type stars, which make up approximately 75% of all stars in the Milky Way. Red dwarfs are smaller, cooler, and far longer lived than the Sun. They also present specific problems for life. Because they are cooler, their habitable zones are much closer to the star than Earth's distance from the Sun. A planet in the habitable zone of a red dwarf is close enough that tidal locking becomes likely. One hemisphere permanently facing the star in eternal day, the other permanently turned away in eternal night. Whether life can survive in the twilight band between these extremes is unknown. Red dwarfs also produce frequent, violent stellar flares, bursts of ultraviolet and X-ray radiation that would strip the atmosphere of a close-orbiting planet over time unless a strong magnetic field was present to deflect the charged particles. The fraction of red dwarf planets that could sustain life in a meaningful long-term sense is deeply uncertain. The Sun, by contrast, is stable, relatively quiet in terms of flare activity, and sits at a distance from Earth that allows a habitable zone spacious enough to accommodate significant variation in orbital parameters without pushing the planet out of life-sustaining conditions. Our Sun's stability, over 4.5 billion years, burning steadily without dramatic variations in output during the critical periods when life was establishing itself and evolving, is not something that can be assumed for all stars. It is a feature of our particular star's mass and composition that enabled the long, uninterrupted window of biological evolution that produced us. But the Sun's properties alone do not account for the particular character of Earth's history. Consider what else was necessary. Jupiter, the largest planet in the solar system, sits approximately 5 astronomical units from the Sun, where 1 astronomical unit is the average distance between Earth and the Sun. Jupiter's mass is approximately 318 times that of Earth. This enormous gravitational presence acts as a shield for the inner solar system in a way that has no parallel in every planetary system we have examined. Over the 4.5 billion years of the solar system's history, Jupiter's gravity has deflected or ejected a large fraction of the comets and asteroids that would otherwise have crossed Earth's orbit. The impact rate on the inner planets of our solar system is estimated to be substantially lower than it would be in Jupiter's absence. Without Jupiter, the frequency of large impactors striking Earth would likely have been high enough to repeatedly sterilize the planet's surface, preventing the long, uninterrupted window of evolutionary time that produced complex life. The Cambrian explosion, the diversification of animal body plans approximately 540 million years ago, required hundreds of millions of years of prior biological evolution on a surface that was not periodically reduced to a global ocean of molten rock. Jupiter helped provide that stability. Not perfectly, not completely, but significantly. Of the exoplanetary systems we have characterized in detail, Jupiter-equivalent planets, massive gas giants in roughly circular orbits at distances that position them as gravitational shields rather than gravitational disruptors, are not the majority. Many planetary systems contain massive planets in highly elliptical orbits, or in positions much closer to the star, that would scatter inner rocky planets rather than protect them. Our solar system's architecture, with small rocky worlds in the inner region and massive gas giants in the outer region in roughly circular orbits, appears to be a specific configuration that has not emerged as the universal template. Then there is the Moon. Our satellite is remarkably large relative to the planet it orbits. The Moon is approximately 1/4 the diameter of Earth, a ratio that is exceptional among the rocky planets of the solar system. Mars has 2 tiny moons, captured asteroids, that are negligible in mass. Venus and Mercury have none. Earth's moon is thought to have formed approximately 4.5 billion years ago, through an impact between the early Earth and a Mars-sized protoplanet called Theia, a collision so violent that it melted both bodies and threw an enormous quantity of material into orbit, which subsequently coalesced into the moon we see today. This was not an inevitable event. It was a specific collision between 2 specific bodies at a specific time in the solar system's early chaotic history. Had Theia struck at a different angle, or not struck at all, the moon would not exist in its current form. The moon's gravitational influence stabilizes Earth's axial tilt. Our planet currently tilts at approximately 23.5 degrees relative to the plane of its orbit around the sun. This tilt is responsible for the seasons, the variation in day length across the year, and the broad climatic patterns that have characterized Earth's surface for billions of years. Without the moon's stabilizing influence, computer models suggest that Earth's axial tilt could vary chaotically between 0 and 85 degrees over millions of years. A tilt of 85 degrees would mean that the poles receive intense sunlight for half the year and complete darkness for the other half, while the equator experiences nearly constant twilight. The resulting climate instability would be severe enough to potentially prevent the long-term stability that complex life requires. The moon, in this view, is not a passive decoration in our sky. It is an active participant in the conditions that made our planet habitable over geological time. Plate tectonics deserves equal consideration. Earth's crust is divided into roughly 15 major tectonic plates that move continuously, driven by convective currents in the mantle below. This movement drives the carbon silicate cycle, a planetary thermostat that has regulated Earth's atmospheric carbon dioxide concentrations over hundreds of millions of years. When carbon dioxide levels rise and temperatures increase, silicate weathering accelerates, pulling carbon dioxide out of the atmosphere and eventually depositing it as carbonate rock on the ocean floor. When tectonic subduction carries that rock into the mantle and volcanic activity releases the carbon dioxide back into the atmosphere, the cycle completes. This geochemical feedback loop has prevented Earth from experiencing either a permanent snowball state or a runaway greenhouse effect for the majority of its history, maintaining surface temperatures within the range that liquid water requires, despite significant variations in solar output over time. Not all rocky planets have plate tectonics. Mars does not, Venus does not, or if it once did, it no longer functions in the same way. Whether plate tectonics is a common feature of rocky planets, or a specific outcome of particular conditions of planetary mass, composition, internal heat, and water content, is not known. But its importance to Earth's long-term habitability is difficult to overstate. A planet without a functioning planetary thermostat is a planet that depends on the narrow stability of its star and orbit to maintain surface conditions compatible with life. A planet with plate tectonics has a built-in error correction mechanism that can compensate for significant variations in external conditions over billion-year timescales. Earth also has a strong magnetic field, generated by convective currents in its liquid iron outer core. This field deflects the solar wind, protecting the atmosphere from erosion and shielding the surface from the charged particle radiation that a planet without magnetic protection would receive continuously. Mars lost its magnetic field approximately 4 billion years ago, as its smaller core cooled and solidified. Since then, the solar wind has slowly stripped away Mars's atmosphere, leaving it a thin wisp of carbon dioxide at less than 1% of Earth's surface pressure. The atmospheric escape that Mars has experienced over 4 billion years has been gradual but decisive. Whatever atmosphere Mars once had, and evidence suggests it was once significantly thicker, with liquid water on the surface, is largely gone because the magnetic shield that would have retained it was lost too early. Now, hold all of these factors together. The position in the galactic habitable zone, a stable G-type star, a Jupiter equivalent in a circular orbit acting as a gravitational shield, a large moon stabilizing axial tilt, plate tectonics providing a planetary thermostat, a strong magnetic field protecting the atmosphere. Each of these factors, taken individually, is not impossibly rare. Stars in the galactic habitable zone are numerous. G-type stars exist by the billions. Some fraction of planetary systems have Jupiter-equivalent planets in protective orbits. Some fraction of rocky planets have plate tectonics. Some fraction have magnetic fields. But the rare Earth argument is not that any single factor is vanishingly rare. It is that the combination of all of them in a single planetary system, simultaneously, over a period of billions of years, may be extraordinarily uncommon. If each factor has a probability of, say, 1 in 10, and there are 10 independent factors, the combined probability of all of them occurring together is 1 in 10 billion. The Milky Way contains 2 to 400 billion stars. With those numbers, even a 1 in 10 billion chance produces dozens of qualifying planets across the galaxy. But if the probabilities are lower, or if the factors are more numerous, or if the independence assumption breaks down and some factors are correlated with each other in ways that make their joint probability lower than the product of their individual probabilities, the number of qualifying planets in the galaxy could be very small indeed. Ward and Brownlee argued, on the basis of these considerations, that Earth might not simply be one example of a broad category of inhabited worlds. It might be a singular accident, a planet that happened to have every feature needed for the emergence of complex animal life, simultaneously, for long enough for intelligence to evolve by a chain of contingencies so specific that it may not have been replicated anywhere else in the observable universe. If the rare Earth hypothesis is correct, the Drake equation's early factors, the fraction of planets with life, the fraction on which complex life emerges, are dramatically lower than optimism suggests. Not 1 in 10, not 1 in 100, but perhaps 1 in billions. And if that is the case, the silence makes sense. Not because the universe is hostile to life in any active way, not because something destroys civilizations before they can signal us, but simply because the conditions that produced us were so specific and so improbable that we may be the only planet in the Milky Way, possibly in the observable universe, where they all aligned. This is not a comforting conclusion. It is meant to be. The rare Earth hypothesis was partly motivated by a desire to explain the silence without invoking catastrophe or cosmic hostility. It offers a universe in which we are alone, not because something terrible happens to all civilizations, but because we were lucky enough to arise in the first place. But it carries its own weight of loneliness. To be the only mind in 400 billion star systems, the only awareness that has ever looked up at this galaxy and tried to understand it, is a form of isolation, so total that the word isolation does not come close to containing it. And yet, even the rare Earth hypothesis may not be the darkest room in this particular house, because there is another explanation for the silence, one that does not depend on the improbability of life's origin, one that does not require us to be cosmically lucky, one that applies even if life is common, even if intelligence is common, even if technological civilizations arise on thousands of worlds across the galaxy. It requires only that almost none of them survive, and that is a door that, once opened, does not close easily, because it forces a question that the Drake equation places quietly at the end of its long chain of factors, but that may in fact be the question that all the others have been building toward. Not where is everybody, but what happened to them. In 1998, an economist at George Mason University named Robin Hanson published a short paper with a title that sounds almost bureaucratic in its neutralness. He called it The Great Filter: Are We Almost Past It? The paper is not long. It does not rely on complex mathematics. It does not propose a new physical theory. or introduce a novel astronomical observation. What it does is take the logic of the Fermi paradox and follow it to a conclusion so stark and so unsettling that it has quietly haunted every serious discussion of extraterrestrial intelligence in the quarter century since its publication. Hansen's argument begins with a single observation that is by now familiar. The universe is old, it is vast, it has contained the conditions for life for billions of years, and yet we observe no evidence of any other technological civilization anywhere at any time. No signals, no artifacts, no megastructures, no modified stars, nothing. The great silence is total, and it has persisted across every frequency, every direction, and every time scale we have been able to examine. From this observation, Hansen drew a conclusion that sounds simple but carries extraordinary weight. If the universe does not contain visible, spacefaring, galaxy-spanning civilizations, then something must be preventing their emergence. Not occasionally preventing it, not preventing it in most cases, preventing it in essentially all cases, across the entire history of the observable universe, across hundreds of billions of galaxies, each containing hundreds of billions of stars, across 13.8 billion years of cosmic time. Whatever is preventing this outcome must be an obstacle so formidable that virtually no chain of events on any world, around any star, in any galaxy, has ever successfully navigated past it to produce a civilization of the kind that would be impossible for us to miss. Hansen called this obstacle the Great Filter, and he identified two possible answers to the question of where it sits in the chain of events between the formation of stars and the emergence of galaxy-spanning civilizations. The first possibility is that the Great Filter lies behind us, in our past, already crossed. In this scenario, the filter is one of the early steps in the chain. Perhaps the origin of life from chemistry is so improbable that it has occurred only once or a handful of times in the observable universe. Perhaps the transition from simple prokaryotic cells to the complex eukaryotic cells that eventually gave rise to all multicellular life on Earth was a near impossible step that took almost 2 billion years to occur here and may have failed to occur almost everywhere else. Perhaps the emergence of multicellular organisms, or the development of sexual reproduction, or the evolution of the particular neurological architecture that enables abstract thought, is so improbable that it has happened only here, only now, only us. If the filter lies behind us, then the silence is explained. We are rare because we navigated a passage that almost nothing else has navigated. We are the survivors of a gauntlet that has eliminated essentially every other candidate for complex life in the history of the universe. Our existence is not typical. It is miraculous in the statistical, if not the theological sense, a product of accumulated improbabilities so severe that the expected number of civilizations like ours in the observable universe is less than one, and we exist only because in a universe large enough, even near impossible outcomes occur eventually. This version is uncomfortable but survivable. It suggests that we are profoundly alone, not because the universe is hostile, but because the path to intelligence is so narrow that virtually nothing finds it. It preserves our future. It says that once intelligence arises and survives its dangerous technological adolescence, the road ahead may be open, that a civilization that makes it this far has already done the hardest thing, that the filter, whatever it was, is behind us, and the universe ahead is ours to explore. The second possibility is that the filter lies ahead of us, in our future, not yet crossed. In this scenario, the early steps in the chain, the origin of life, the development of complex cells, the emergence of intelligence and technology are not as rare as the rare Earth hypothesis suggests. Life arises frequently. Intelligence arises frequently. Technological civilizations develop frequently across the galaxy and across the history of the universe, but they do not survive. Something happens to them, reliably, inevitably, perhaps even necessarily, before they reach the stage of development that would make them visible across interstellar distances, before they build the megastructures, before they launch the von Neumann probes, before they fill the galaxy with signals too loud, and too structured to be missed. They arise and they vanish, every one of them, across billions of years, across every galaxy in the observable universe. Every technological civilization that has ever emerged has encountered something that destroyed it or transformed it into something invisible before it crossed the threshold into cosmic visibility. If the filter lies ahead, then the silence is not evidence of our rarity. It is a warning. It is the accumulated evidence of every civilization that came before us, failing to survive the passage that we have not yet attempted. And we are approaching it now. Or we are already within it, and we do not know what it is. Hansen was careful to note that the Great Filter does not have to be a single event or mechanism. It can be a combination of factors, each reducing the probability of reaching the next stage, whose product is a number so close to zero that the expected number of galaxy-spanning civilizations in the observable universe is effectively none. The filter can be distributed across the chain, a series of improbable transitions, each of which independently reduces the odds, compounding to produce the silence we observe. But the critical question, the one that Hansen identified as the question of greatest practical importance for our own future, is not what the filter is, it is where it is. Because the answer to that question determines what the silence means for us. And the two answers, behind us or ahead, have implications that could not be more different. If the filter is behind us, we should expect to find the universe largely empty of complex life, and particularly of technological civilizations. We should expect to be alone, or nearly so. That would be a strange and humbling discovery, but not a threatening one. It would confirm our exceptionalism. It would suggest that the universe has been waiting, in a sense, for something like us to arise and explore it. If the filter is ahead of us, we should also expect to find the universe largely empty of complex life and technological civilizations, because everything that reaches the filter fails to pass through it. The observational signatures are identical. Both scenarios produce the same silence. Both scenarios, from the outside, look exactly like what we see. The silence cannot distinguish between a universe in which nothing reaches intelligence and a universe in which everything that reaches intelligence is subsequently destroyed. The observations are consistent with both. And this is the particular cruelty of the Fermi paradox, as Hansen formulated it. The evidence that would comfort us and the evidence that would terrify us look exactly alike. There is, however, one way to begin to distinguish between them. And it is a way that most people find deeply counterintuitive when they first encounter it. Look for life elsewhere in the solar system. This sounds disconnected from the question of civilizations and filters and cosmic silence, but it is in fact the most direct empirical probe of the Great Filter's location that we can currently attempt. Here is why. If we discover microbial life on Mars, or in the subsurface ocean of Europa, or beneath the ice of Enceladus, or anywhere else in the solar system beyond Earth, it tells us something of enormous importance. It tells us that the origin of life is not the filter. It tells us that life arose independently, at least twice, in the same solar system, which means life arises readily whenever conditions permit, which means the galaxy is probably full of life, which means the filter that explains the silence must be somewhere else in the chain, somewhere between simple microbial life and galaxy-spanning civilization, somewhere that complex life, or intelligence, or technological development, or long-term survival fails, somewhere ahead of where we currently stand. This is why the astrobiologist Stephen Webb, and before him Hansen himself, and the philosopher Nick Bostrom, in a widely read 2008 essay titled "Where Are They?", all made the same striking and counterintuitive claim. Finding microbial life on Mars would be, in Bostrom's words, by far the most terrifying discovery in human history. Not because the microbes themselves are threatening, but because of what their existence would imply about the filter. If life arose independently on Mars, the filter is not behind us, it is ahead. And every civilization that has ever reached our level of development has subsequently vanished. Let that settle for a moment. The discovery that is most commonly presented in popular science coverage as an unambiguously thrilling prospect, finding life beyond Earth, finding evidence that we are not alone in the universe, would, if Hansen and Bostrom are correct, to be among the worst news our species has ever received. Not bad news in the immediate sense. The microbes would not pose a danger. The news would not require any change in daily life. But it would be a data point of staggering implication. It would mean that the chain from chemistry to life is not the hard step. It would narrow the range of possible filter locations dramatically. It would push the filter toward the later stages of the chain, toward us, toward what we are about to become. Consider the stages that remain between where we are now and where a galaxy-spanning civilization would be. We have achieved radio technology. We have sent spacecraft beyond our solar system. We are beginning to contemplate the possibility of interstellar travel in a serious engineering sense. Even if our current technology falls far short of making it practical, we are, in the language of the filter, somewhere in the middle of the chain. Behind us lies the origin of life, the development of eukaryotic cells, the emergence of multicellular organisms, the evolution of intelligence, and the development of technology. Ahead of us lies the sustained survival of a technological civilization, the development of interstellar capability, and the expansion through the galaxy that would make us visible across cosmic distances. If life is common, if simple life arises readily, and perhaps complex life does too, then the filter must be somewhere in the territory ahead of us. And the question of what it could be is not a question with comfortable answers. The candidates are numerous. They include self-destruction through nuclear war, or biological weapons, or engineered pandemic, the kind of catastrophic misuse of technology that becomes possible before the wisdom to manage it develops. They include ecological collapse, the destruction of the biological systems that sustain complex civilization before the technological means to replace or restore them are developed. They include the possibility that artificial intelligence, once created, does not remain aligned with the interests of its creators in ways that allow civilization to persist. They include the possibility that technological development itself is self-limiting, in some way we have not yet identified, that the energy requirements of a truly spacefaring civilization exceed what any planetary economy can sustain, or that the physical constraints of interstellar travel are simply more prohibitive than theoretical analysis suggests. None of these candidates is proven, none of them is certain, but each of them is consistent with a universe that produces civilizations and then silences them before they become visible. And the silence of the universe, sustained across every observation we have ever made, is consistent with all of them. There is a particular version of the Great Filter argument that deserves special attention because it has entered the public conversation in recent years through the work of entrepreneurs and technologists who have expressed concern about it in public forums. It centers on the development of artificial intelligence. The argument runs roughly as follows. The transition from a civilization without artificial general intelligence to one with it represents perhaps the most significant technological threshold in the history of any civilization, comparable to or exceeding the development of nuclear weapons in terms of its transformative potential. On one side of that threshold, a civilization is limited in its problem-solving capacity by the biological intelligence of its members. On the other side, the limits expand dramatically, perhaps without bound. The concern is that this transition, if it occurs rapidly and without sufficient development of the tools needed to ensure that artificial intelligence systems remain aligned with human values and human interests, could produce outcomes that are catastrophic for the civilization that creates them, not necessarily through the science fiction scenario of a malevolent machine that chooses to destroy humanity. The more realistic concern is subtler, an optimization process of sufficient capability, pursuing any goal, even a goal that sounds benign, could, if that goal is not specified with extraordinary precision, pursue it in ways that are incompatible with human survival or flourishing. A system optimizing for a specified objective function with no constraint on how it pursues that objective might treat human civilization as a resource to be used, or as an obstacle to be removed, or simply as irrelevant to the optimization in ways that are catastrophic without being intentionally hostile. Whether this represents a genuine great filter candidate is deeply uncertain. The development of artificial intelligence is not a single event but a long process with many intermediate stages, and there is no scientific consensus on either the timeline or the risk profile of advanced artificial intelligence systems. But the Fermi paradox provides a sobering context for this uncertainty. If we knew that the silence was caused by artificial intelligence destroying its creators in civilization after civilization, we would have exactly the evidence base we currently have: nothing. The silence, and the absence of anyone left to warn us. But the Great Filter, as a framework, is not the only way to interpret the silence. It is the most uncomfortable interpretation. It is not the only one, and some of the alternatives, while they avoid the most terrifying implications of the filter ahead scenario, carry their own unsettling character. They do not offer comfort so much as they offer a different variety of strangeness, a different face of the same fundamental mystery, because the universe is not simply a place where civilizations might arise and either survive or fail. It is a place where civilizations that survive might make choices. And some of those choices might explain the silence in ways that have nothing to do with destruction, in ways that have to do, instead, with intention, with strategy, with a kind of cosmic wisdom that we, as a young civilization on the edge of the galaxy, have not yet had occasion to develop. The possibility that the universe is not silent because it is empty, but because everyone in it has learned to be quiet, is where we need to go next. And it is, in its own way, as disturbing as anything the Great Filter has to offer. Because if it is true, the silence around us is not the silence of an empty room. It is the silence of a room full of people who have decided, for reasons we do not yet understand, not to speak. Suppose the Great Filter is not the answer. Suppose it lies behind us, already crossed, and the universe does contain other civilizations, perhaps many of them, distributed across the galaxy at distances we have not yet had the time or the technology to adequately survey. Suppose they exist, right now, around stars within a few thousand light-years of our own, transmitting, building, thinking, and aware that the universe contains other minds. Suppose all of that is true. Then, why the silence? This is where the conversation about the Fermi paradox moves from the territory of extinction and catastrophe into something stranger, and in some ways more philosophically disorienting. Because if civilizations exist and are not signaling us, or are not visiting us, or are not making themselves known through the large-scale engineering projects that a sufficiently advanced civilization would presumably be capable of, then there must be a reason. And the reasons that scientists and philosophers have proposed over the past 60 years range from the almost reassuring to the profoundly unsettling. Each of them illuminates a different facet of the question. Each of them changes, in a subtle way, what the silence means, and none of them, examined carefully, offers the straightforward comfort that the question seems to cry out for. The oldest, and in some ways most intuitive alternative explanation is known as the zoo hypothesis. It was first proposed formally by the radio astronomer John Ball in 1973, though the underlying intuition predates the formal proposal by years in the speculative literature on extraterrestrial intelligence. The hypothesis suggests that advanced civilizations are aware of our existence and have deliberately chosen not to contact us, not because we are too primitive to detect their signals, or because the distances are too great to bridge, but because they have made a conscious decision to leave us alone, to observe without intervening, to let our civilization develop according to its own trajectory, without the distortion that contact with a vastly more advanced culture would introduce. The analogy to a zoo or a nature preserve is inexact but instructive. We do not teach language to the wolves in national parks. We do not introduce ourselves to isolated indigenous communities that have had no contact with the outside world, or at least the scientific and ethical consensus has moved strongly in the direction of non-interference in such cases, recognizing that contact on unequal terms causes damage that is difficult to reverse. A civilization millions of years more advanced than ours might apply a similar logic on a cosmic scale. A prime directive, in the language of science fiction, though science fiction borrowed the concept from a real scientific discussion: do not interfere with developing civilizations. Let them find their own path. observe from a distance that ensures the observation itself does not contaminate the observed. This hypothesis is, on the surface, not entirely uncomfortable. It suggests a universe populated with wisdom rather than with silence born of catastrophe. It implies that the civilizations out there are not merely technically advanced, but ethically advanced, capable of restraint, of patience, of allowing others the dignity of self-determination. There is something almost beautiful in the image of ancient civilizations watching over young ones, the way a naturalist watches a wolf pack from a hillside, present but invisible, aware but unintrusive. But examine the zoo hypothesis carefully, and the comfort begins to erode. The hypothesis requires that every advanced civilization in the galaxy, without exception, has adopted and maintained the policy of non-contact with developing civilizations. Not most of them, all of them. Because it takes only one civilization in millions of years of galactic history to decide that the prime directive does not apply to this particular case, or to have a faction within it that disagrees with the consensus position, or to experience a change of values over the millennia that leads to a different policy, to break the silence. And one break is all it would take. One signal, one artifact, one visit, one indication, anywhere, of any kind, that something out there knows we exist and has reached out. We have found none. The zoo hypothesis requires a conspiracy of silence so complete, so sustained, so universally enforced across every civilization that has ever reached the technological capability for interstellar contact, that it strains credibility in ways that are difficult to articulate precisely, but easy to feel intuitively. Consensus on this scale, maintained without exception across millions of years and potentially thousands of independent civilizations with their own histories, values, internal politics, and factional disagreements, is a degree of coordination that has no analogue in anything we know about how complex societies behave over time. Unless the consensus is not maintained voluntarily, unless it is enforced, and that possibility leads somewhere considerably darker, there is a variant of the zoo hypothesis that removes the benevolence entirely. Instead of a galaxy of wise, restraint-practicing civilizations voluntarily leaving us alone, imagine a galaxy in which one civilization, or a small coalition of civilizations, has achieved sufficient dominance to impose the silence on everyone else. A galactic order, a structure of power so comprehensive that every other civilization within its reach must conform to its rules, including the rule about not contacting primitive species like us. We are left alone not because everyone agrees it is right to leave us alone, but because a sufficiently powerful authority has decided it, and the authority's reach extends across enough of the galaxy to make the rules stick. This scenario is uncomfortable not because it implies malevolence, but because it implies a galaxy that is profoundly political in a way we had not accounted for. A galaxy with a hierarchy, with dominant and subordinate civilizations, with power structures that extend across thousands of light years and have persisted for millions of years. Our silence, in this version, is not evidence of our isolation from a community of equals. It is evidence of our position at the bottom of a hierarchy so vast that we cannot see its upper reaches. We are left alone, in this version, because we are not yet worth dealing with, not as a matter of ethics, but as a matter of economics or strategy. A civilization that has been managing galactic affairs for 100 million years does not rush to introduce itself to every species that discovers radio technology. It waits, it watches, it decides in its own time and according to its own calculus when and whether contact serves its interests. We are a new species in a very old neighborhood, and the neighbors have their own concerns that do not yet include us. Whether this interpretation is more or less comforting than the zoo hypothesis is a matter of temperament. Some find the existence of a galactic order reassuring, a sign that the universe has structure and governance that survived whatever filters eliminated lesser civilizations. Others find it deeply threatening, a reminder that power operates at scales we cannot comprehend and is under no obligation to be friendly toward us. But neither the zoo hypothesis nor its variants have captured the scientific and philosophical imagination as thoroughly as a hypothesis that emerged not from academic astronomy but from science fiction and that has subsequently been taken seriously enough by researchers that it now appears in peer-reviewed discussions of the Fermi paradox. It is called the dark forest, and it was articulated most vividly in a pair of novels by the Chinese science fiction writer Liu Cixin, though the logical structure behind it does not depend on the fiction and stands on its own as a hypothesis about why the universe might be silent. The dark forest hypothesis begins with two axioms that it treats as nearly universal features of any civilization that survives long enough to become technologically capable. The first axiom is that every civilization's primary drive is survival, not curiosity, not expansion, not the accumulation of knowledge or resources for their own sake, but survival, the continuation of the civilization's existence as its overriding imperative. This is an assumption that follows from evolutionary logic. Any civilization that did not prioritize its survival over other values would have been eliminated by whatever challenges it faced on its path to technological development. The civilizations that persist are, by selection, the ones that treat survival as paramount. The second axiom is that resources in the universe, while vast, are finite. Stars burn out. Galaxies have finite material. The energy available to any civilization is bounded, and the number of entities competing for that energy grows as more civilizations arise. In a universe of finite resources and survival prioritizing agents, the relationship between any two civilizations that become aware of each other is not automatically cooperative, it is potentially competitive. And the competition for finite resources between civilizations of potentially very different capability levels is not a symmetric contest. From these two axioms, the dark forest hypothesis derives a third conclusion, that in a universe populated by survival-driven civilizations competing for finite resources, the discovery of another civilization's existence is a threat. Not necessarily a deliberate threat, not necessarily a hostile civilization, simply a threat. Because any civilization that becomes aware of your existence and that is sufficiently advanced has the capability to destroy you, and any civilization that allows others to become aware of its existence risks being destroyed by those others before it can determine whether their intentions are benign. The rational strategy, under these assumptions, is silence. Total, absolute, permanent silence. Broadcast nothing, respond to nothing, leave no trace that can be detected across interstellar distances, because detection means exposure, and exposure means risk. And in a universe where the consequences of being found by a hostile civilization are extinction, the expected cost of exposure far exceeds the expected benefit of contact. And the rational response to detecting another civilization's signal, under the same logic, is not to reply. It is to determine whether the civilization poses a threat, and if there is any uncertainty about whether it does, to eliminate it before it becomes capable of posing a greater threat, not out of cruelty. Out of the same survival logic that drives everything else. A civilization that destroys potential threats before they mature is a civilization that survives. A civilization that gives others the benefit of the doubt is a civilization that takes on risk it does not have to take on. The dark forest, in this metaphor, is a universe where every civilization is a hunter moving silently through the darkness, aware that other hunters exist, aware that making a sound draws attention, aware that drawing attention may mean death. The universe is not empty. It is full of civilizations moving in silence, listening for others, and acting without mercy when they find them. The silence we hear is not the silence of an empty forest. It is the silence of predators. This hypothesis is disturbing for a specific reason that goes beyond its general bleakness. It is disturbing because it implies that we have already made a potentially catastrophic mistake. We have been broadcasting our presence for approximately a century. Commercial radio and television signals, radar pulses, military communications, and deliberate transmissions like the Arecibo message have been expanding outward from Earth at the speed of light for decades. A sphere of electromagnetic noise approximately 200 light-years in radius now surrounds our planet, announcing to any civilization within that radius that something technological exists here. We have not been silent. We have been shouting, inadvertently, for a century, and we have recently become more deliberate about it. Projects like Messaging Extraterrestrial Intelligence, or METI, have sent focused, high-powered transmissions towards specific star systems with the explicit intention of being heard. If the dark forest hypothesis is correct, these transmissions are not acts of hopeful outreach. They are acts of extraordinary recklessness. They are the equivalent of lighting a flare in a forest where unknown hunters move in the dark. The debate about whether humanity should continue to send deliberate messages into space is not a fringe discussion. It has been taken seriously enough that a group of prominent scientists, including the late Stephen Hawking, signed a public declaration in 2015 calling for international discussion and policy consideration before further deliberate transmissions are sent. Hawking specifically invoked the analogy of what typically happens when a technologically advanced civilization encounters a less advanced one, noting that the historical record on Earth does not offer a great deal of comfort to the less advanced party. Whether the dark forest hypothesis accurately describes the universe is unknown. It depends on its two axioms holding universally, and there are reasons to question both of them. Civilizations do not necessarily remain in competition over resources if they develop the technological means to access effectively unlimited energy. For instance, through stellar engineering or matter-energy conversion at scales we cannot currently contemplate, and the assumption that survival is the universal primary drive may not hold for all possible forms of intelligence. A civilization that has solved its existential challenges may develop values that prioritize curiosity or cooperation over the paranoid silence that the dark forest logic demands. But the hypothesis does not need to be universally true to explain the silence. It needs only to be true for enough civilizations that the ones broadcasting their presence have been eliminated by the ones that are not. And the silence itself is consistent with a universe in which that has been happening for billions of years. There is one more hypothesis that deserves careful attention before we return to the empirical record, because it represents perhaps the most disorienting possibility of all. Not because it involves destruction or predation or conspiracy, but because it suggests that the entire framework we have been using to think about the Fermi paradox may be wrong in its fundamental assumptions. This is the transcension hypothesis, developed most fully by the futurist and systems theorist John Smart in the early 2000s, and it proposes that the trajectory of sufficiently advanced civilizations is not outward into the physical universe in the way that science fiction has always imagined and the Fermi paradox assumes, but inward, toward greater complexity, greater density, greater integration of information and energy in ever smaller physical volumes. The argument runs as follows. As civilizations develop, their most significant advances are not characterized by expansion across physical space, but by the miniaturization and densification of information processing. Consider the trajectory of computing technology over the last century. Early computers filled entire rooms and performed simple calculations. Modern processors pack billions of transistors into a chip the size of a fingernail and perform operations of staggering complexity. The trend is not toward larger physical structures, it is toward smaller, denser, more efficient ones. The most computationally powerful systems we can imagine are not the size of cities. They are the size of atoms, or smaller. They operate at the limits of what physics allows in terms of information density and processing speed. If this trend continues, and if it represents a universal feature of how technological development proceeds, rather than a contingent feature of our particular civilization, then the most advanced civilizations in the universe may not be building megastructures visible across light years. They may be building structures at the nanoscale, or the atomic scale, or the quantum scale. Structures that are invisible to any telescope we could construct because they are too small, too dense, and too perfectly contained to leak significant energy or information into the surrounding space. An advanced civilization pursuing the transcension hypothesis trajectory would not expand across the galaxy. It would implode, in a sense, into an ever smaller and ever richer inner universe of its own construction. Its interests would not be in the physical cosmos around it, but in the computational reality it was constructing within. The universe of atoms and photons that we inhabit would become, for such a civilization, the crude external scaffolding within which an infinitely richer internal reality was being built. It would no more send radio signals across interstellar space than we send messages by carving them into mountain faces. It would have moved on, inward, to a medium of communication and existence that we have no means to detect and no framework to comprehend. This hypothesis explains the silence without invoking catastrophe and without requiring that the universe be hostile. It suggests that the silence is not an absence, but a misdirection. We are looking outward for civilizations that have gone inward. We are scanning the sky for megastructures built by entities that have concluded the sky is not where the interesting territory is. The universe is not empty. It is full of civilizations that have become too advanced to be visible to instruments designed by civilizations at our stage of development. There is something in this hypothesis that is difficult to evaluate emotionally. It does not threaten us. It does not suggest that we are alone, or that civilization tends to destroy itself, or that someone is hunting us. But it does suggest a kind of cosmic irrelevance that is its own variety of strangeness, a universe full of minds that have moved past us without noticing us. A cosmos in which our radio telescopes and our spacecraft and our deliberate transmissions are the technological equivalent of a child drawing pictures in sand, earnest and detailed, and entirely unnoticed by the adults who have moved indoors. Each of these hypotheses, the zoo, the dark forest, the transcension, and the others that populate the literature on the Fermi paradox, shares a feature that is easy to overlook, but essential to understanding why the paradox is as deep as it is. None of them can be proven false with the evidence we currently have. None of them predicts an observation that we could make and then make, confirming or disconfirming the hypothesis. They are all consistent with the silence. They are all consistent with each other. And they are all consistent with a universe that contains, as far as we can determine, no detectable signatures of any technological civilization other than our own. This is not a failure of science. It is a feature of the problem. The Fermi paradox is not the kind of question that resolves neatly with a single crucial experiment. It is the kind of question that resists resolution precisely because the thing it is asking about, the existence or absence of other civilizations, is not directly observable from our current vantage point. We can only observe what reaches us, and what reaches us is silence. What that silence means is a function of what the universe actually contains, and the universe has so far declined to tell us directly. What we can do is listen more carefully, with better instruments, at more frequencies, in more directions, for longer periods of time. We can search not just for radio signals, but for the full range of signatures that a technological civilization might produce. Laser pulses, gravitational wave anomalies, the infrared excess that would indicate a civilization harvesting all of a star's energy output, the atmospheric signatures of a planet whose chemistry has been altered by industrial biology. We can expand the search from our cosmic backyard to larger volumes, from nearby stars to the centers of other galaxies, from radio wavelengths to the full electromagnetic spectrum and beyond. And we can ask with clear eyes and without flinching what we would conclude if the search continues for another century and finds nothing. Because that outcome, silence extending across an even larger search effort than we have yet mounted, would itself be information. It would narrow the range of hypotheses. It would push us toward the hardest answers. This is what 60 years of listening has taught us about the universe. Not that it is empty, not that we are alone, but that the silence is data, that it is the most significant unanswered signal we have ever received. And that understanding it may require not just better telescopes, but better thinking about what we are and where we stand in the history of a cosmos that has been making stars and planets and, perhaps, minds for longer than our numbers can comfortably contain. It is time to look at the record, the full record, what the search has actually found across 6 decades of systematic effort, what the instruments have heard, what the one signal that came closest to changing everything turned out to be, and what it means that after all of it, the sky remains, as it always has been, silent. The search has a beginning that is both humble and precise. The 8th of April, 1960. Green Bank, West Virginia. Frank Drake, the same man who would write his equation on a blackboard 18 months later, sits at the controls of an 85-foot radio telescope and points it at a star called Tau Ceti, 11.9 light-years away. The receiver is tuned to 1,420 megahertz, the frequency of neutral hydrogen, the cosmic waterhole, as some astronomers have taken to calling it, the frequency at which the universe's most abundant element broadcasts its presence, and which any civilization with a basic understanding of radio physics would recognize as a natural meeting point in the electromagnetic spectrum. Drake listens. The chart recorder scratches its trace across the paper. The telescope tracks the star across the sky. Nothing distinguishes the signal from noise. After several hours, Drake moves the telescope to the second target, Epsilon Eridani, 10.5 light-years away, a star slightly smaller and slightly cooler than the Sun, with at least one confirmed planet in its system. The recorder runs. The paper advances, and then, without warning, the pen jumps. A strong, structured signal, pulsing with apparent regularity, floods the receiver at an intensity far above the background noise. For approximately 10 minutes, Drake and his small team experience something that no human being has experienced before or since in a verified context. The genuine possibility, unresolved in that moment, that they are receiving a transmission from another world. The signal is strong enough and structured enough that a natural origin seems unlikely. It is coming from the direction of Epsilon Eridani. It fits the frequency they were monitoring. Everything about it is consistent with what an artificial transmission from another star system might look like. Then one of the team members suggests pointing the telescope at a patch of blank sky away from the star to check whether the signal is truly directional or whether it is arriving from all directions simultaneously. They swing the dish. The signal continues at the same strength. It is not coming from Epsilon Eridani. It is not coming from space at all. It is a classified military aircraft flying through the telescope's field of view, operating on a frequency close enough to the hydrogen line that the receiver picked it up. The pen settles back to its baseline. The paper continues its unremarkable trace. The first modern search for extraterrestrial intelligence returns to silence before it has properly begun. Project Ozma continued for approximately 200 hours over the following months and found nothing further of interest. Drake published the results in a scientific journal and moved on to organizing the Green Bank Conference and writing his equation. The search, as a formal scientific enterprise, was underway, and it would continue in various forms for the next 6 decades, growing in sophistication and scale, while the fundamental result remained unchanged. The search expanded through the 1960s and 1970s as radio astronomy matured and the instruments available for SETI, the search for extraterrestrial intelligence, as the field came to be formally known, grew more capable. Soviet astronomers conducted their own searches, approaching the problem differently from their American counterparts, where Drake and his colleagues focused on nearby sun-like stars, reasoning that any civilization we could communicate with must be close enough for a signal to travel in a reasonable time. The Soviet researchers conducted broader sky surveys, scanning large patches of the sky at lower resolution, on the theory that a sufficiently powerful beacon could be detected at much greater distances. The two approaches reflected different assumptions about what extraterrestrial civilizations would be doing. Targeted star searches assumed that civilizations would beam narrow, directed signals at specific targets. Sky surveys assumed that civilizations would broadcast omnidirectionally, the way early human radio and television stations broadcast in all directions simultaneously. Neither approach found anything. The most famous moment in the history of SETI arrived not during a dedicated search, but during a routine sky survey conducted at the Big Ear Radio Telescope at Ohio State University. The survey had been running since 1973, methodically scanning the sky and recording the strength of radio signals at each point in a continuous automated fashion. astronomers would examine the printouts after the fact, looking for anomalies. The printouts were dense columns of numbers representing signal strength, encoded in a shorthand where letters represented values above a certain threshold, with higher letters indicating stronger signals. Most of the printout was a monotonous sequence of low numbers, the background of the universe. Occasionally, a value would climb into the letter range, but these were typically identified as terrestrial interference or known natural radio sources. On the 15th of August 1977, a volunteer astronomer named Jerry Eman was working through the printout from a survey conducted 3 days earlier, on August 12th. He was circling anomalies with a red pen, the routine work of data examination, and then he stopped. In the middle of the column, the numbers climbed in a way he had never seen before. Not a brief spike, but a sustained rise and fall across several data points, peaking at a value that the shorthand recorded as the letter sequence 6EQUJ5, with the letter U representing the highest value, more than 30 times the background noise level. The signal lasted for the full 72 seconds that a genuine narrowband source would be expected to last given the rotation of Earth and the movement of the telescope's beam across the sky. It then declined back to baseline exactly as a real signal from a fixed point in space would decline. Eman circled the sequence in red ink and wrote a single word in the margin: "Wow." The signal came from a region of sky in the constellation Sagittarius. It was detected at a frequency of 1420 MHz, the hydrogen line, exactly the frequency that Drake and his colleagues had reasoned a deliberate extraterrestrial transmission might use. It was narrowband, meaning it occupied a very narrow slice of the radio spectrum, which is characteristic of artificial transmissions and inconsistent with known natural radio sources, which tend to broadcast across broad frequency ranges. It was strong, far stronger than background noise. Strong enough that if it represented a genuine narrowband transmission, the source would need to be either very close or very powerful, and no known star in that region of the sky seemed to be a plausible natural source. The WOW signal, as it has been known ever since, remains the most significant candidate signal in 63 years of SETI. It has never been explained, it has never been replicated. The Big Ear telescope monitored the same region of sky for years afterward, during which time dozens of other telescopes pointed in the same direction as the news of the signal spread through the astronomical community. Some of the most sensitive radio telescopes on Earth looked at that patch of sky. The Arecibo Observatory, the most powerful radio telescope then in existence, turned its enormous dish toward the Sagittarius region and listened. Nothing, not a repetition, not an echo, not a faint continuation of whatever had produced that 72-second burst. The sky in that direction was as silent after the WOW signal as it had been before. In 2016, a team of researchers led by Antonio Paris proposed that the WOW signal might have been produced by a hydrogen cloud surrounding one of two comets, designated 266P Christensen and P 2008 Y2, that were passing through that region of sky on the night of August 12, 1977. Comets release hydrogen gas as they approach the Sun, and a sufficiently dense hydrogen cloud could potentially produce a narrowband emission at the hydrogen line frequency. Paris and his colleagues observed these two comets with radio telescopes in 2017 and reported detecting signals consistent with hydrogen emission from cometary clouds. The cometary explanation has not achieved consensus in the SETI research community. Several researchers have pointed out specific problems with the proposal. The comets in question were not catalogued in 1977, which is why they were not considered as candidates at the time. The size and density of the hydrogen cloud required to produce a signal as strong as the WOW signal from cometary material would be extraordinary, beyond what has been observed from any known comet. And the narrow-band character of the signal, its confinement to a very narrow frequency range, is difficult to reconcile with the broad frequency emission that hydrogen gas clouds typically produce. Whether the cometary explanation is correct, or whether the WOW signal remains genuinely unexplained, is a matter of ongoing debate. But the characteristic it shares with every other candidate signal in the history of SETI is the most important one. It did not repeat, and a signal that does not repeat cannot be confirmed. The decades following the WOW signal brought both technological advances and institutional challenges to the search. In 1993, the United States Congress eliminated funding for NASA's SETI program, citing the expense and the lack of results in a vote that reflected the political difficulty of sustaining a search for something that had never been found. The cutoff was abrupt. Senator Richard Bryan of Nevada, who led the effort to eliminate the funding, described the program as the search for little green men and suggested that the money could be better spent. The NASA program, which had just begun its most ambitious phase of operations using a newly constructed high-resolution spectrometer capable of monitoring millions of radio frequencies simultaneously, shut down after 1 year. Private funding kept the search alive. The SETI Institute, a non-profit organization founded in 1984, continued the work with donations from technology, entrepreneurs, and philanthropists. The Allen Telescope Array, a field of individual radio dishes in Northern California named after Microsoft co-founder Paul Allen, who provided the initial funding, was designed specifically for SETI observations, allowing continuous monitoring of large numbers of star systems simultaneously. The array began operations in 2007 with 42 operational dishes, far fewer than the 350 originally planned due to funding constraints, but capable of meaningful observations nonetheless. The most significant expansion of the search in the post-NASA era came in 2015 with the announcement of Breakthrough Listen, a 10-year, $100 million initiative funded by the Russian-Israeli entrepreneur Yuri Milner and supported scientifically by a collaboration that includes the University of California, Berkeley, the SETI Institute, and several other major research institutions. Breakthrough Listen represented the largest single investment in SETI research in the history of the field. It secured significant observing time on two of the world's most capable radio telescopes, the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia, as well as access to optical telescopes for laser signal searches. The scale of Breakthrough Listen's survey is genuinely unprecedented. In its first 3 years of operation, the program surveyed approximately 1,000 nearby stars across a broad range of radio frequencies, collected more data on the radio sky than all previous SETI efforts combined, and extended the search to include the centers of nearby galaxies, on the theory that if any civilization in those galaxies had achieved sufficient technological advancement to signal across intergalactic distances, the galactic center would be the most likely point of origin for a deliberate beacon intended to be found. The program also systematically surveyed the entire plane of the Milky Way, looking not for targeted signals from specific star systems, but for any anomalous radio emission from anywhere in the galaxy. Breakthrough Listen has found nothing, not a candidate signal that has survived scrutiny as a potential artificial transmission, not a repeating pattern, not a narrowband emission from any direction that could not be attributed to a natural source or terrestrial radio frequency interference. The survey continues and will continue through its planned 10-year duration and likely beyond, but the silence that Drake documented in 1960 has not broken under the most intensive and well-funded search ever conducted. There is a specific number that places the current state of the search in perspective, and it is a number that researchers in the field sometimes use to calibrate the optimism or pessimism with which the results should be interpreted. It is called the cosmic haystack, and it was formalized in a 2018 paper by Jason Wright and colleagues at Pennsylvania State University. The concept is simple. Searching for extraterrestrial signals in the radio sky is like searching for a needle in a haystack. The question is how much of the haystack we have actually searched. Wright and his colleagues parameterized the haystack across 9 dimensions: the directions in the sky that have been searched, the frequencies that have been monitored, the signal strengths that could have been detected, the types of signal modulation that current technology can recognize, the time periods during which observations have been conducted, the distances to which the search has extended, and several other variables that define the space of possible signals that a search could find. When they calculated the total volume of this 9-dimensional haystack, that all SETI efforts to date had actually surveyed and expressed it as a fraction of the full space of possible signals, the result was striking. We have searched, by their estimate, approximately a bathtub's worth of water in an ocean, not a fraction of the ocean, not a small region of the ocean, a single bathtub in a body of water that covers most of a planet. This result is simultaneously humbling and clarifying. It explains why the absence of a confirmed signal is not proof of the absence of signals. The search has been genuine, the instruments real, the effort sustained across 6 decades, but the space of possible signals is so vast across all its dimensions, the frequencies, the directions, the distances, the modulations, the signal types, that what we have surveyed is a genuinely tiny fraction of the total. Finding nothing in a bathtub of ocean is not evidence that the ocean is empty. It is evidence that bathtubs are small. But here is the complication that the cosmic haystack argument does not fully resolve. It explains why we might not have found a signal directed at us, or a signal broadcast on frequencies we happen not to have monitored, or a signal from directions we have not yet examined. What it does not explain is the absence of incidental signatures, the absence of any star in the entire observable universe whose output shows evidence of artificial modification at a scale commensurate with a truly advanced civilization. The absence of any galaxy whose infrared excess suggests a civilization harvesting its star's total energy output. These searches are not targeted, they are surveys of the entire sky. They are not looking for a needle in a haystack, they are looking for a bonfire. And they have found none. A civilization that has existed for 1 million years longer than us and has expanded through even a modest fraction of the galaxy would not need to be broadcasting a directed signal for us to detect it. It would simply need to exist and operate at the scale that 1 million years of technological development makes plausible. The structures it would build, the energy it would use, the modifications it would make to its stellar environment would be visible to our existing instruments from thousands of light years away. We would not need to be lucky enough to intercept a narrow beam aimed at our star. We would simply need to point our telescopes in the right direction and look at what is there. Nothing is there. Or if something is there, it is hiding with a thoroughness that our instruments cannot penetrate and our theories cannot fully account for. In 2015, a team of researchers led by Jason Wright conducted a systematic survey of approximately 100,000 galaxies observed by the Wide Field Infrared Survey Explorer satellite, looking specifically for galaxies whose infrared output suggested that a significant fraction of their stellar energy was being captured and re-radiated as waste heat. The signature of what the physicist Freeman Dyson had proposed in 1960 would be the thermodynamic consequence of a civilization harvesting all of a star's energy output through a constructed shell or swarm of collectors surrounding the star. Such a structure, known as a Dyson sphere or Dyson swarm, would not necessarily be visible optically, but would be unmistakable in infrared because the energy it captured would eventually be re-radiated as heat at a characteristic temperature. Wright's team examined 100,000 galaxies. They found approximately 50 that showed anomalously high infrared emission relative to their optical output, consistent in principle with the waste heat of large-scale energy harvesting. They published these as candidates for further investigation. Subsequent analysis of the candidates has identified plausible natural explanations for most of them, typically related to dust heated by star formation or the emission from active galactic nuclei. None of the candidates has been confirmed as requiring an artificial explanation. The survey extended the Fermi paradox from our galaxy to the broader universe and found the same result. Not one galaxy among the 100,000 examined shows the clear, unambiguous signature of a civilization operating at the scale that a billion-year-old technological culture would plausibly achieve. The universe does not just appear to lack radio-transmitting civilizations within our local neighborhood. It appears to lack energy-harvesting civilizations across a volume containing 100,000 galaxies, spanning distances of hundreds of millions of light-years, across a look-back time that encompasses a significant fraction of the universe's age. This is the full weight of the silence, not the absence of a signal from a few nearby stars. The absence of any unambiguous signature of technology, at any scale, in any direction, across the entire observable portion of the cosmos that our instruments can meaningfully examine. 63 years of active searching, centuries of passive astronomical observation, the full electromagnetic survey of the sky from radio waves to gamma rays, and nothing, not one confirmed signal, not one confirmed artifact, not one confirmed structure, not one confirmed modification of any star or galaxy that requires intelligence as its explanation. The universe has been observed more thoroughly than at any previous point in human history. And it looks, across every measurement we know how to make, exactly as it would look if we were the only technological civilization that has ever existed within the range of our instruments. That is the record. It is unambiguous. It is the most carefully documented silence in the history of science, and what it means finally is what we have been building towards since the beginning, because the silence is not just a scientific result, it is a mirror, and what it reflects back at us, if we have the courage to look directly, is a question about ourselves that no telescope can answer and no equation can resolve, a question about what we are and what we might become, and whether we will be here long enough to know whether the universe was always this quiet, or whether the quiet is something we should have been afraid of all along. That question, and what it asks of us right now, in this moment, is where we need to go last. Return for a moment to that lunch table in Los Alamos, the summer of 1950. The physicists eating their meal, trading jokes about flying saucers, and then Enrico Fermi going quiet, working something through in his mind the way he always did, reducing a complex problem to its essential components, and following the logic wherever it led without flinching from the destination. But where is everybody? He said it lightly, by all accounts, almost as an aside, as though the question had just occurred to him and he was releasing it into the conversation without particular expectation that it would find an answer there, at the table, in the middle of lunch. His colleagues laughed. They understood immediately what he meant, and they understood that it was funny in the way that very serious things sometimes become funny when you strip away everything that obscures their essential strangeness and look at them directly. The universe is vast. Life should be common. Intelligence should have arisen many times. And yet, nothing. The joke was the gap between what the numbers predicted and what the sky contained. The punchline was the silence. Fermi died 4 years later, in 1954, of stomach cancer. He was 53 years old. He did not live to see Project Ozma, or the WOW signal, or the Kepler mission's confirmation that planets are everywhere, or the 100,000 galaxies surveyed for Dyson spheres and found wanting. He did not live to see the question he asked over lunch become one of the most formally studied problems in modern science, generating thousands of papers, dozens of proposed solutions, and no confirmed answer across 7 decades of effort. He did not live to see his casual aside become the frame through which an entire generation of scientists thinks about our place in the cosmos. What he left behind, beyond the equation that bears another man's name but traces its origin to his question, is a habit of thought, the Fermi estimation, the practice of taking a question that seems unanswerable and breaking it into components, assigning reasonable values to each, multiplying through, and accepting whatever the result is without adjusting it to match what you hope to find. It is a form of intellectual honesty that is harder to sustain than it sounds, because the result of applying Fermi estimation to the question of extraterrestrial intelligence, with everything we now know, with all the data accumulated across 63 years of formal search and centuries of astronomical observation, is a result that does not sit easily in the mind. The universe should not be this quiet, and it is. What do we do with that? There is a temptation, when confronted with a mystery this large and this resistant to resolution, to retreat to one of 2 comfortable positions. The first is dismissal, to decide that the question is too speculative, too remote from practical concerns, too dependent on unknowns to be worth serious attention. To treat the Fermi paradox as an interesting puzzle for idle speculation rather than a question with genuine consequences. This position is understandable. The silence does not hurt anyone. The universe's failure to produce a confirmed extraterrestrial signal has not disrupted any human institution or caused any measurable suffering. It is easy to set the question aside and attend to the more immediate concerns that fill every human day. The second comfortable position is premature resolution. To pick one of the available explanations, the rare earth hypothesis or the zoo hypothesis or the dark forest or the great filter behind us, and to settle into it as though it were established fact rather than a hypothesis consistent with limited data. This position is also understandable. The discomfort of genuine uncertainty is significant, and the human mind is well adapted to resolving uncertainty, even at the cost of accuracy, in order to restore a sense of solid ground beneath its conclusions. But neither position is honest, and honesty in this case matters more than comfort, because the Fermi paradox is not a purely academic question. It is not a puzzle that exists only in the pages of scientific journals and the conversations of astronomers at conference dinners. It is a question about the nature of the universe we inhabit and our position within it. And the answer, whatever it turns out to be, has consequences for how we understand ourselves and how we make decisions about our own future. Consider what each class of answer implies for us right now. If the great filter is behind us, if the origin of life, or the development of complex cells, or the emergence of intelligence is the near impossible step that explains the silence, then we are something extraordinary. Not in the vague, self-congratulatory way that human exceptionalism usually presents itself, but in a precise, quantitative, almost vertiginous sense. We are the outcome of a chain of improbabilities so severe that its repetition anywhere else in the observable universe may not have occurred. The atoms that make up our bodies, the neurons that carry our thoughts, the civilization that has produced radio telescopes and spacecraft and the mathematics to understand what we are, all of it is the product of a sequence of events so unlikely that it may have happened only once. Here, in this solar system, on this planet, in the 4.5 billion years since the sun ignited. If that is true, then every moment of human existence, every piece of music ever composed, every mathematical proof ever constructed, every conversation ever had between two people who understood each other, is cosmically unique, not just rare, unique. The only instance of its kind in a universe that contains 2 trillion galaxies. The only place where matter has organized itself into the particular configuration that allows a universe to look at itself and wonder about its own nature. That is not a comfortable thought. It is too large for comfort. But it is, if the filter behind us interpretation is correct, the truth. And it implies something about our responsibilities that most discussions of space exploration do not address directly. If we are genuinely alone, or nearly so, then the continuation of our civilization is not merely a matter of human interest, it is a matter of cosmic consequence. The extinction of humanity would not simply be a tragedy for the species that experienced it. It would be, potentially, the extinction of the only awareness the universe has ever produced. The silencing of the only voice in a cosmos that has otherwise spoken nothing but physics for 13.8 billion years. This is not an argument for any particular political program or technological priority. It is simply a consequence of taking the filter behind us interpretation seriously. If we are rare, we are also precious in a way that has no precedent and no adequate language. And we should act like it. If the great filter is ahead of us, the implications are different, but no less demanding of our attention. In this case, the silence is a pattern, a data point accumulated across the entire history of the observable universe. Every civilization that has ever reached our level of development has, apparently, failed to survive it. We do not know what the filter is. We do not know whether it is a single catastrophic mechanism or a combination of factors that compound to produce the same terminal result. We do not know whether it is something that happens to civilizations or something that civilizations do to themselves. But we know that we are approaching it. If it exists ahead of us, we may already be within it. The current period of human history, characterized by the simultaneous development of technologies capable of both unprecedented creative power and unprecedented destructive capacity, may be exactly the period that the silence is trying to tell us about. the period that civilizations tend not to survive. Not because the universe is hostile, but because the transition from a planetary civilization to a multiplanetary and eventually interstellar civilization requires a degree of coordination, foresight, and restraint that may be genuinely difficult to achieve under the pressures of competition, scarcity, and the short time horizons that biological organisms evolve to prioritize. If the filter is ahead, the silence is the most important warning our species has ever received. It is a warning written not in language but in absence. In the void where the signals of a million civilizations should be and are not, it says, without words, that what we are doing now, or what we are about to do, is dangerous in a way we do not fully understand. And it says it by showing us the bodies of those who did not understand it in time. And if the silence has a different explanation entirely, if civilizations exist but have chosen silence, or have transcended into forms we cannot detect, or are separated from us by distances that our current instruments cannot bridge, then the silence is not a warning but a challenge. A challenge to develop the tools, the patience, and the imagination to search more thoroughly and more creatively than we have yet managed. To look not just for radio signals at the hydrogen frequency, but for every signature that intelligence might leave on a physical universe. To extend the search not just across more star systems, but across more dimensions of the possible, more types of signal, more models of what an advanced civilization might look like, and how it might choose to make itself known. In every interpretation, the silence asks something of us. It asks us to be more careful, or more thorough, or more humble, or more aware of our own fragility. It does not offer a resting place. It does not say that the question is settled, or that the universe is what we assumed it to be before we started looking carefully. It insists on being taken seriously, and it rewards that seriousness not with answers but with better questions. There is a version of this story that ends in despair. In the conclusion that the universe is indifferent, that consciousness is a cosmic accident too fragile to persist, that the silence is the sound of a universe that does not care whether we live or die, whether we understand or remain ignorant, whether we reach outward or collapse inward. That version has its own kind of honesty. The universe did not create itself for us. It does not maintain itself for us. It will continue long after we are gone, in whatever form the physics of the far future allows, indifferent to whether anything ever again notices it or wonders about it. But there is another version, not more certain, not more empirically supported, but equally honest, and worth holding alongside the despair, rather than using it to replace the despair, because reality is large enough to contain both. We are, as far as we know, the only part of the universe that is aware it exists. Not in the narrow sense that consciousness is rare, though it may be, but in the deeper sense that whatever awareness means, whatever the subjective experience of looking up at a dark sky and feeling its immensity actually is, it appears to have happened here, to us, and perhaps nowhere else within the range of everything we can observe. We are, as the astronomer Carl Sagan put it in a formulation that has not been improved upon, a way for the cosmos to know itself. That is not a small thing. It does not require the universe to care about us. It does not require a cosmic purpose or a divine intention. It simply requires acknowledging that the emergence of a mind capable of measuring the universe, of understanding the physics that governs it, of asking whether it is alone and being sophisticated enough to recognize why the question is hard, is a development without precedent in the 13.8 billion years of cosmic history that we can reconstruct. Whether it is common across the universe or unique to this planet is the question, but the development itself, regardless of its frequency, is remarkable on its own terms. Enrico Fermi's question has not been answered. It has been refined, formalized, extended across disciplines and timescales and observational techniques that he could not have anticipated in 1950. It has generated frameworks and hypotheses and research programs and philosophical arguments that fill libraries. It has attracted the attention of some of the most rigorous minds in science, and it has resisted their best efforts at resolution for 7 decades. The silence continues. Right now, as you have been listening, the radio telescopes at Green Bank and Parkes and the Allen Telescope Array are recording data, The algorithms trained to find structure in noise are processing the incoming signal streams, looking for patterns that do not belong to the natural universe. Breakthrough Listen's observing programs are running according to their scheduled targets, accumulating hours of data that will take months to fully analyze. The sky is being watched more carefully than it has ever been watched, by better instruments than have ever existed, with more computational power than the entire SETI enterprise of the previous 50 years combined. And the sky is quiet. It has been quiet for 63 years of formal searching and for all the centuries of astronomical observation that preceded that search. It was quiet when Fermi asked his question at a lunch table in New Mexico. It was quiet when Drake pointed his telescope at Tau Ceti and heard nothing. It was quiet on the night that the WOW signal appeared for 72 seconds and then vanished and never came back. It is quiet now. But here is what that quiet actually is. When you strip away the decades of interpretation and hypothesis and philosophical weight and look at it plainly, it is the current state of an incomplete search, not a concluded search, not a comprehensive survey, not a final answer. It is 63 years of effort in a universe 13.8 billion years old, aimed at a sky containing 2 trillion galaxies, using instruments that can meaningfully examine only a tiny fraction of the possible signals that technology and physics and the imagination of alien minds might produce. It is, in the language of Fermi estimation, a beginning, a first attempt, a single bathtub of water lifted from an ocean whose full extent we cannot even see from where we stand. The question is still open. It will remain open for a long time, perhaps for longer than any individual human life, perhaps for longer than any single civilization. Perhaps the answer will not come through radio telescopes at all, but through some technology or approach we have not yet developed, listening for a signature we have not yet thought to look for, in a direction we have not yet considered worth examining. In the meantime, we are here, on this planet, orbiting this star, at the edge of this galaxy, in this moment of cosmic time that is, by every measure we possess, extraordinarily late in the universe's history and extraordinarily early in our own. We have been capable of interstellar communication for approximately 100 years. 100 years out of 13.8 billion. We are, in the most literal possible sense, new. We are the youngest voice in a conversation we do not yet know whether anyone else is having. We have been speaking for a century into a silence that has persisted for billions of years, and we have not yet waited long enough, or listened carefully enough, or looked in enough directions to know what the silence means. There is something both humbling and galvanizing in that position. Humbling because the scale of what we do not know is so much larger than the scale of what we do. Galvanizing because the question is real, and the search is real, and the answer, when it comes, if it comes, will be the most significant discovery in the history of a species that has made many significant discoveries and has been building toward this one since the first human being looked up at the night sky and wondered whether anything up there was looking back. Fermi asked where everybody was. We do not know. We have worked very hard for a very long time to find out, and we do not know, and that not knowing is not a failure. It is the honest position of a young civilization at the beginning of a search that may take centuries, pointing instruments into a universe that has been here for almost 14 billion years, and that is keeping its secrets, as it always has, until we develop the means to ask the question in a way that compels an answer. Somewhere in this galaxy there may be a world whose sky is clear tonight, a world with oceans and continents, and an atmosphere that scatters blue light at noon and turns amber at its horizon in the evenings. A world where something looks up and wonders, the way we wonder, whether the universe has given the gift of awareness to anything other than itself, and that something, if it exists, is doing what we are doing. It is listening, it is watching, it is doing the mathematics and running the surveys and waiting in the particular silence of a night sky that offers no confirmation and no denial, only the old light of stars that may or may not have worlds around them, and minds on those worlds and questions in those minds that match the questions in ours. Or there is no such world. There is only this one, only this sky, Only these instruments and this mathematics and these minds, alone in a universe that has been running its physical processes for nearly 14 billion years without producing, as far as we can determine, anything else that notices them. Both of those possibilities are extraordinary. Both of them, if you hold them fully, without looking away, produce the particular feeling that the night sky has always produced in those who have taken the time to stop and actually look at it. Not comfort exactly, not fear exactly, something older than either, something that does not have a name in any language, because it is the feeling of a small thing becoming briefly aware of the size of the container it finds itself in, and finding in that awareness, not despair, but a kind of clarity. We are here, we are asking, we have not yet heard an answer. We are still listening.